Hello. Hope you're all doing well. All right. So today we move on to chapter 8. And in it, we're looking at the two-body central force problem. So I'm just going to give a brief overview, and then we'll just get to problem solving as usual. So the idea is that we have an isolated system with just 2 point masses, m1 and m2. And because it's isolated, the only thing that they have to interact with are each other. So there is some potential energy, and we're sticking with potential energies that only depend on position. So this would depend on position of particle 1 and position of particle 2. But it turns out we can actually simplify this a lot further. So certainly to start with, we say that, okay, well, the Lagrangian would be T1 plus T2 minus U. And this is the potential energy of the two of them together. So minus U12. And because this is an isolated system, it means that even if I were to take both particles and just shift them, if I shift them both the same amount in the same direction, then nothing changes. If they were in an external field, that need not be true, right? Because if there was an external field, that might be a non-uniform field, and then it would depend upon where they are in that non-uniform field. So shifting the system would change things. But here, because they're isolated, the only thing they interact with each other is each other. So shifting both of them, keeping that relationship the same, changes nothing. So what that tells us then is that the potential energy should only depend on the difference of R1 minus R2. Furthermore, if we say that the force is conservative, well, which it has a potential energy, so we have a conservative force that depends only on the separation, it turns out to be spherically symmetric as well. So in fact, this only depends on the magnitude of R1 minus R2. So this suggests that we should describe the problem in terms of this relative position vector, R1 minus R2. So we are going to change our coordinates. Instead of using just R1 and R2 as our configuration variables, we're going to use this relative separation vector. And then we need another one, and it turns out that the useful one to use is the position of the center of mass, which, since it's just 2 point masses, we know is M1R1 plus M2R2 over M1 plus M2. So these are our new generalized coordinates. And we see that we haven't really lost any information because before R1 had 3 components, R2 had 3 components, so we needed 6 bits of information. And now using the relative separation vector R and the position of the center of mass, again, each of them has 3 components, so we still need 6 configuration degrees of freedom. It further turns out, though, as we go look further into the system, that because the angular momentum is conserved, we will see that the motion takes place in a plane. So we might as well reorient ourselves so that it's in the xy plane. And so we don't need a third coordinate, so we can knock one off. If we aren't interested in how the center of mass is moving, we can just focus on the relative separation. So we've gone from 6 to 3 first by just focusing on we're not worrying about the center of mass, we're just looking at the motion of the 2 objects about the center of mass. And then we further reduce it because we realize that we can always make it lie in a plane. And so then that brings us down to 2. So we should be able to describe our system using just 2 variables, which end up conveniently being r and phi. So if we follow through the transformations of shifting from R1 and R2 to these variables, it turns out that our Lagrangian ends up splitting very naturally into 2 parts. One is the Lagrangian for the center of mass. And since there is no external field of any kind, the only contribution to the center of mass ends up being the kinetic energy. So we have 1/2 big M being the total mass, r dot being the velocity of the center of mass squared. And then here for the relative portion, we have 1/2 mu r dot squared minus u of r. And I should clarify, sorry, these are both vectors, right? These are both vectors. This one is just the scalar quantity r.
Sorry, quick question. What is mu?
So mu is the reduced mass. So in the process of switching from R1 and R2 to these two, because of the presence of the masses in this position of the center of mass, it turns out that the mu here is the reduced mass, which is basically M1 times M2 over M1 plus M2.
Okay. Thank you.
So what has happened? We're looking at these 2 objects, and there's no external force. The center of mass is just going to continue with the constant velocity of the center of mass, so the momentum of the system is conserved. And so we move to the center of mass frame, and then what we see are these 2 objects orbiting. So what we would see is the center of mass somewhere between them, and they are both orbiting about the center of mass. And because the center of mass always has to lie on the line joining them, that in fact tells us that they are always exactly opposite to each other on opposite sides of the center of mass. Right? So as this is moving here, M2 will be moving here, and so they'll be describing orbits and staying on either side of the center of mass. And the size of the orbit, of course, depends on the relative masses. So for example, we say the Earth goes around the sun, but in reality, the Earth and the sun go around the center of mass. It's just that the sun is so much more massive than the Earth that we don't notice the motion of the sun. But there is a slight wiggle. And if we looked at a system instead where you have a massive planet very close to the sun, what people these days call hot Jupiters, then the center of mass of that planet star system is substantially closer to the surface or even outside the surface of the star, so that you can clearly see that both the planet is orbiting around the center of mass and the star is also orbiting around the center of mass. And we can detect that wiggle. And that is in fact one of the ways that they detect planets outside the solar system, is by looking for that rhythmic wiggle in the motion of the star. And I'm sure our astro majors can give us more detail on that. But yeah. So right now I've kept it very general. This is always saying is that it is a potential energy that depends on the relative separation and is central. Sorry, that was the other thing. If it is central, then it has to, and conservative, it has to be spherically symmetric. This was shown in chapter 4. If U/F is spheric, central, and conservative, it tells us that it is spherically symmetric. So that's why it only depended on the magnitude of R1 minus R2 and not on the direction of R1 minus R2. But right now it's completely general. It could be a force that goes as R squared. It could be a force that goes as 1 over R, or potential energy rather. And so if we focus on electrostatics or on gravity, where U of R does go as 1 over R, then we call this the Kepler problem, because Kepler was the first person to do extensive studies on this problem with regards to the solar system. All right, I won't, well, no, okay. So let me see. All right, so if we focus on just the relative part of the Lagrangian, what we see is that 1/2 mu r vector dot squared is naturally going to break down into 1/2 mu r dot squared plus r phi dot whole squared, like this, so just in polar coordinates. And so we have altogether 1/2 mu r dot squared plus r phi dot whole squared minus u of r. And we can do the usual Euler-Lagrange stuff. And what we find, unsurprisingly, is that for the phi equation, we see that angular momentum is conserved. And so we can relate phi dot to L. And let me see, the particular relation that we have is mu, mu r squared phi dot is equal to the angular momentum L. MVR, yes, okay. And so we can replace phi dot in terms of L. So we have that. And then once we have this relation, we can go back to our Lagrangian and plug it in. And now we have a Lagrangian which is purely in terms of R and R dot. And so we've reduced it to a one-dimensional problem. And so that leads us to the types of energy diagrams that we've seen before, where you have something like this. U is a function of R. And except what we're actually plotting here is U effective, because we see that we not only have this R dot kinetic energy term, we're going to pick up an R term from plugging in for phi dot, right? So we have an R term here, and we have U of R. So it makes sense to just lump them together into an effective potential, which combines the true potential plus this angular momentum term. So effective potential is the true potential plus what we'll call the centrifugal potential energy. And that's what makes it go back up again. Because if it was just the true potential, that would be, in the gravitational case, for example, that would just be minus 1 over r. So that would just go down like this. But what we'll see is that the centrifugal term actually causes it to shoot up as long as the angular momentum is non-zero. All right, and so then once we have this, we can do all the stuff we like to do with energy diagrams. We can talk about bounded orbits. And so here, this would be an orbit going between r min and r max. We can talk about circular orbits. We can talk about unbounded orbits. If you have more energy, you can actually escape out to infinity.
Quick question. On the right side of your page, it says U effective is equal to U of R plus something?
Yes, UCF, the CF standing for centrifugal.
Okay, got it.
And that centrifugal term comes from plugging in this expression for phi dot over here. Other questions? All right. So yeah, so we can talk about bounded and unbounded orbits, and R min and R max. But we shouldn't forget that this is still 2D motion. It is still happening in the R phi plane. So this allows us to, we can use all the tricks that we learned back in chapter 4 to figure out, for example, the time it takes to go from R max to R min back to R max, right? So the time it takes for one oscillation, if you like, in the R direction. But how long does it take to go from phi equals 0 all the way back to phi equals 2 pi? How long does it take to do that? That period doesn't have to be the same as the period for the R oscillation. So if they are the same, then what you end up with is what is called a closed orbit, where it just nicely repeats itself again and again. But if the periods are slightly different, what you end up with is a precessing orbit, where you end up with something like this, where the values of R min and R max stay the same, but the angle keeps shifting so that the orbit as a whole is precessing. And it turns out that perfectly closed orbits are very special cases. They only happen in 2 cases, in fact. So they only happen if you have U is proportional to -1 over R, or if you have U is proportional to R squared. These 2 will give you perfectly closed orbits, and everything else does not. And so you might think that, oh, well, then our solar system should have closed orbits. But no, it doesn't, for 2 reasons. One is, even if you're working in Newtonian gravity, the effects of the other planets spoils it. It's not an isolated 2-body system. All the other planets have effects as well. And these perturbations create an effective potential, which is no longer just 1 over R. It has additional terms. The other reason why is that even after astronomers accounted for all these effects of the other planets, they found that there was a precession in Mercury's orbit that they couldn't account for. And so for some time, they were speculating about a planet closer to the sun than Mercury called Vulcan. And they were looking for it, but they never found it. And in the end, that precession was explained by Einstein's theory of general relativity, because GR in the large limit certainly reduces to Newtonian gravity. But if you're very close to a massive object, you start to see the effective terms which are different from Newtonian gravity. And these differences lead to additional terms. It's not just 1 over R now, or 1 over R squared in the force. You get higher order terms. And the effect of that leads to the precession of the orbit of Mercury. All right, that was my general overview. Any questions before we get to problem solving? Okay, a few general things. So for the next few weeks at least, because you will be starting to also work on your papers and such, at least for the next few weeks, we'll keep the problem solving groups the same as your paper groups, so that if you finish early on the problem solving, you can discuss stuff about the paper. Also, I reached out to the writing workshop, and they do remote consultations. So what I ask is that between April 13 to April 23rd, that someone in your group reaches out with a draft of your paper and talks to the writing workshop, so that if they have any like general suggestions or comments about how to make it look even better, that please do that. Yeah, okay. All right, so I'll list the problem numbers here, and I'll also go to Moodle and type those up. And then I'll call out names one by one, and you can tell me who's in your group, in your paper group, and I'll put you all in a breakout room. All right, yeah, let's start with those.